Alright, welcome to the first screencast for Guidesheet number 7. We're going to take everything we've done so far and put it together to look at breaking down and putting back together circuits that have both series and parallel combinations. So first, a quick review of some of the basics. In parallel combinations, all items must have the same potential difference, delta V, and then the total resistance must be less than the smallest of the resistors. In a series combination, all the items must have the exact same current, okay, not potential difference, and then the smaller resistors will have the smallest changes in potential. Delta V, the potential difference will be the smallest. Okay, so first we look at these first four. These are all parallel combinations. I can tell that because they are parallel physically to each other. There's a junction, so there's more than one place for the current to come in and current to come out. The overall resistance would be equal to 1 over the first one plus 1 over the second one plus however many we have. Now a shortcut for that, because of the way the fractions work out, if they're both the same, you can take how many you have and divide that into the value of each resistor. So in this case, they're each worth 4 ohms, and I have 2 of them. So as a group, they're going to be worth 2. In this one, they're each worth 8 ohms, and I also have 2 of them, so these are going to be worth 4. Now notice that's smaller than the smallest resistor, and it is less. It gets less. If I add another one on, it's going to become even smaller. 8 divided by 3 would be smaller than 8 divided by 2. So it's kind of a paradox in that you add resistors and yet the resistance goes down. Now for the ones where it's not equal, then you'll need to use the 1 over r. The easiest way to do that is with an x to the minus 1 key on a calculator. 4 x to the minus 1 plus 8 x to the minus 1. Now take that, that's equal. But that's only equal to 1 over RT. So I'm not done yet. I got to take that also to the minus 1 as my last step. So as a group, these are worth essentially 2.7 ohms. And if you go over here and look at the other one, then we would take 6 x to the minus 1 plus 8 x to the minus 1. Yep, didn't plus sign. Let's just go ahead and clear that. So 6 x to the minus 1 plus, there we go, 8 x to the minus 1 and equals. And again, we're not done. We've got to take that x to the minus 1 one more time. That is the inverse of the actual resistance. So 3.4 ohms. Now it's larger than the first one was, but both the cases they're smaller than the smallest one. Okay, if you can do that, you're in pretty good shape with any circuit that's in combination with series groups as well, because essentially the trick will be, the first thing you want to do is determine what's going on with any parallel combinations and simply replace them with what they're equivalent to, and then figure it out as a series circuit. So here's what I mean. So in this example, I've got 2 and 4, just like the one we had above. We know that together those are worth 2 ohms. Now that means this circuit would be equivalent to 2 ohm resistors that were in series with each other, because I can replace the 2 parallel 4 ohm resistors with one resistor that's worth 2 ohms. That's why we often refer to it as equivalent resistance. That makes the total resistance of this circuit 2 plus 2, or 4 ohms. From Ohm's law, I is equal to V over R. So 12 divided by 4 will be 3 amps. Now since this one here's the current coming out, there's no place for it to go, this one must measure 3 amps. Now at this junction it's going to split. Now these two have to add up to 3 amps. Now in this case, both of those individual resistors were the same, so that means 1.5 and 1.5. And we've been able to find all the currents. And the other thing we can do is check the potential differences to make sure that everything adds up. So in any one loop of a circuit, the potential difference that we put in, 12 in this case, should be equal to that we use up. Well, in this one, we use up V is equal to I times R, so 2 times 3, we use up 6 volts at this one. Now here, an electron will either go this way or on the upper path. So I don't need to find both, I just need to find one or the other. 1.5 times 4 is 6. And 6 plus 6 is 12. So all the voltage we used up in any one loop is equal to all the voltage we put in. This circuit is complete. We know all the currents, all the potential differences. Again, if this is 6 volts, this has to be 6 volts. They have to be the same. They're in parallel. So we would say that we put in 12 volts. Potential difference, that's our measure of our energy we're putting in, and we would use up 12 volts in any loop of the circuit. Okay, so you'd follow that same process every time. It's just a matter of making sure you can identify which parts are parallel. Now, in all 4 of these first ones, they're all the same basic configuration. This time we have 4 and 4, so from above we know that this group is equivalent to 1 2 ohm resistor, exactly the same as we had before. So instead of 2 separate 4s, we could call it 1 2. Now, the 2 ohm is in series with the 4, so 2 plus 4 is a total of 6. Again, I is equal to V over R. 12 divided by 6 is going to be 2 amps. This one's all by itself, so it has to get the full 2 amps. At this point, the current splits up. Half is going to go this way and half is going to go this way. I know it's half and half because I have 2 and they're equal. If they weren't equal, I couldn't do it this way. I'd have to do some more work. But in this case, it's going to be half each way, so it's 1 amp and 1 amp. Now we can do a quick check to see if our potential differences all work out the way they should. Again, we're putting in 12. Here it's V is equal to I times R. 4 times 2 is 8. And then 4 times 1 is 4. Add those together and we get 12. So check. This circuit is also good. Okay, let's do the other two while it's still all fresh in our mind. It should be just as easy. 2 over 2 would be 1 for this group. So it's equivalent to a 1 ohm resistor. 1 plus 2 is 3 for a total equivalent resistance of 3. 12 divided by 3 would be 4 amps. This one's all by itself, so it must get the total. We have a split of 2 equal resistors, so that means this has to be 2 and this has to be 2. 2 times 4 is 8 volts of potential difference here. 2 times 2 is 4 volts potential difference there. 4 plus 8 is equal to 12. Here we have the same basic thing, 2 over 2, that's going to give us 1. Down here we have 4, so that gives us a total of 5. That gives us a total current of 12 divided by 5. It's 2.4. This one must get the full 2.4. At this point it must split. Again, the split is equal in this case because both are the same. Only because they're the same, you can't always say that. So that's 1.2 each way. Now the quick voltage check, potential difference to see if everything's okay. 4 times 2.4 is 9.6. And then 2 times 1.2 is 2.4. 2.4 and 9.6 makes 12, so check, we're good. Okay, so again, every time you analyze a combination circuit, you want to find the parallel portions. You want to replace them with what they are equivalent to. Redraw your circuit and solve it as a series circuit, and then go back and find the individual currents in the parallel portions last. That would be your last step. We'll do some more practice on the other side and wrap that up.